Okay, folks, so we've done an introductory video to differentials. Now I'm going to do two more examples of it. So last time we skipped over question number 15, and now I want to return to it. So this problem is asking us to make a distinction between delta y and differential y. Okay? So as a reminder, I'm not going to be accurate in drawing this graph at all. Let's just say this function looks something like this. Okay, folks, I'm not being accurate in representing this at all. And maybe this is the value 2. And our goal is to figure out what is the value. Well, here's 2.05, and we get this value right here. And so we would call this distance. What's the best way to show this? Let's go ahead and put dashed lines here. We would call this distance right here, this distance is our delta y. Okay? Delta y is the difference in the two y values on the function. Again, remember I said that deltas always go with the functions, differentials go with the tangent lines. So if I came along and at 2 I made a tangent line, okay, then this value right here, when I plug 2.05 into the tangent line, okay, this value right here would give me differential y. And notice that the closer the 2.05 is to the anchor point of 2, the closer differential y will be to delta y, provided this is a well-behaved function. Okay, so that's the picture that's going along with this problem, and that might help guide you through it. So delta y is the one that's more intuitive to find, but in the real world it's also harder to calculate. So delta y is simply f of 2.05 minus f of 2. So plugging 2.05 into our function, we have 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. All of that is that's a little bit of contrast on the eyes. All of that is the f of 2.05, and let's subtract from that f of 2, which is 2 cubed plus 2 squared minus 2 times 2 plus 1. Okay. So I went ahead and crunched this in a calculator, but I think you could make the argument that this would be difficult to calculate by hand. Cubing the number 2.05 would be difficult. Squaring the number 2.05 would be moderately difficult. But I plugged it into a calculator, and we got 9.717625, accurate to 5 decimal places. Minus, and then if I calculate f of 2 here, well, let's see, that's 2 cubed is 8, plus 4, minus 4, so I'm at 8, plus 1 is 9, and so I get that delta y, accurate to 5 decimal places, is 0.717625. Okay. And the idea is, folks, this is this actual distance, the true distance between the y value f of 2 and the y value f of 2.05. But that was fairly difficult to calculate. Okay? We can get a very good approximation by calculating differential y without ever having to do anything harder without having to work with this number 2.05, I guess, is what I'm saying. So we said last time, in the last video, that differential y is equal to f prime of x times differential x, but always that's the same thing as f prime of x delta x. Okay? So let's go ahead and calculate f prime of x for this function. F prime of x is 3x squared plus 2x minus 2. And so if I find f prime of 2, the anchor point that we're basing this off of, we get 3 times 2 squared plus 2 times 2 minus 2, which is, let's see here, well, help me out, this is 4 and 12, plus 4 is 16, minus 2 is 14. Okay, so I get that f prime of 2 is 14. So we'll have f prime of 2 times, what's our delta x? The delta x is the change in the x values, which is 0.05. So that's equal to 14 times 0.05, and if we crunch that, we get 14 times 0.05 is 0.7. Well, notice how close these two values are to each other. That's the point that we're trying to make, that the differential y value is very, very close to the delta y value when we're close to our anchor point here. Okay? So at times it might be very difficult to actually calculate the change in the y values. So instead of calculating delta y, we calculate differential y. And notice that whereas I had to use a calculator, or I guess I didn't have to, but I chose to use a calculator to help me with this much more difficult calculation, I was able to do all of this just, the hardest thing I had to do was multiply 14 times 0.05. There was no power operations at all in this procedure. Okay, so let's look at our very last example. Okay. I am going to make a slight change to this, so this originally said 21 centimeters. I don't know why I've still got that there. I wanted to change that to 20 centimeters. So let's read the problem. The radius of a sphere was measured and found to be 20 centimeters with a possible error measurement of at most 0.05 centimeters. Okay. What is the maximum error using this value of the radius to compute the volume of the sphere? Okay. So somebody's trying to compute the volume of a sphere, right? So to do so, they have to take a guess at what the radius is. So they use their measuring tools, and their measuring tool says, hey, the radius appears to be 20 centimeters, but it's not a perfect instrument, and there's a tolerance, an error in it. So the question is if things were a worst-case scenario, the radius would be what? If we're trying to see what the maximum error would be, we would add 0.05 to the radius. So if that's the worst case, that 20.05 is the radius. You might say, why not go the other way? But it turns out that would give you it would still give you an error, but a smaller error than the error we're about to calculate. So the worst case scenario is we think the radius is 20, but it's actually 20.05. Well, that's only off by 5/100ths of a centimeter, right? We might say that's not a big deal. Well, remember that the volume of the sphere has a cube in it, so the error of 0.05 gets compounded by a power of 3 here, and that can make a big difference in our final calculation. So the question is asking not what is the maximum error in the radius. We know the maximum error in the radius would be 0.05, but what is the maximum error in the volume of the sphere based upon our radius calculation. So here, to find the true answer, let's pause for a second. Let's let x equal the radius. And as you know, that the volume of a sphere as a function of a radius is 4/3 times pi times x cubed, the radius cubed. Okay? So the true answer, what is the maximum error, is v of 20.05 minus v of 20. So if we wanted to get the true answer, we would calculate the volume of the sphere when x is 20.05. We would calculate the volume of the sphere when x is 20, and we'd look at the difference between the two. But personally, I don't want to plug 20.05 into this function, especially because of that cubing operation. So instead of doing this, instead of getting the true answer, we're going to get an approximate answer. Okay. So again, in terms of the notation we used before, this right here would be our delta y. Actually, I guess I should be true to the story problem, and this would be our delta v. The max change in the volume would be the difference between these two. But we're going to say that delta v can be approximated by differential v. Okay. Well, differential v we know is equal to, this is the same thing as before, v prime of x times differential x, which always we just go ahead and say, well, that's the same thing as delta x. Okay? So we're going to calculate v prime of 20 and multiply it by the max error, which is 0.05. Okay? So we said the volume, well, let's just rewrite it one more time. The volume of the sphere was 4/3 pi r cubed. So then the derivative of that will be 4 pi r squared. And if I calculate v prime of 20, I get 4 times pi times 20 squared, which gives me, let's see, 400 times 4, which gives me 1600 pi. So this is 1600 pi, and I'm going to multiply this by 0.05. That's the same thing as 1600 pi times 5 over 100, which, let's see, that 100 goes into there 16 times, and we do 16 times 5. We get 80 pi as our approximation for differential v, which is basically delta v. Okay? I did crunch this beforehand, just so you know. This is approximately 251.3. So in terms of our error in the volume, being off, having a volume, or excuse me, a radius calculation off by a maximum of 20.05 could lead to a difference in the volume of 251.3 centimeters cubed. I think that might be a little bit alarming the first time you do that calculation. We were only off in our radius calculation by 0.05 centimeters, but that has an effect of being off by roughly 251 centimeters cubed, which is a decent amount to be off by, because that error compounded through the operation. Okay? Just so you know, if you actually calculate delta V, which means you actually plug 20.05 into your volumes formula for a sphere and subtract from it the volume at 20, you get approximately 251.96, and you see that our linearization is very, very close to the true answer, accurate within 0.6 centimeters cubed, which isn't too bad. Okay, that's my last example on linear approximations and differentials. I do find these two topics, each one on their own isn't too bad, but as you start working with the two simultaneously, it can be a little bit confusing. So please do look at the unit review, the exam review, and start trying to separate these two types of problems. Let me know if you have any questions. This is my last video for 4.6.